Hi, I'm Mark Barsamian. In this video, I'll be discussing possibility trees and the multiplication rule and permutations. This material is from section 9.2 of the book, and the corresponding homework is this fairly large collection of problems from section 9.2. So let's start by recalling examples from the previous video in which we used tables to illustrate sample spaces. We had the example involving throwing two six-sided dice, one blue die and one red die. So we had this table where this cell, for instance, indicated the roll where the blue die was 3 and the red die was 5. And we had an example involving drawing colored balls from an urn. In the first part of the example, we had drawing with replacement. So, for instance, this cell indicates that the first ball drawn was the red ball labeled R2, and the second ball drawn was the blue ball labeled B1. This cell corresponds to drawing the same ball twice, which is possible because after the first ball is drawn, the ball is put back in the urn, and then the second ball is drawn. This table corresponds to drawing without replacement. So it's impossible to draw the same ball twice. But in some situations, it's not possible to make a table. There may be more steps than can be illustrated in a table, or possibilities for later steps may depend on the outcomes of earlier steps. In these cases, knowing how to make a possibility tree can be very useful. So, for example, consider a situation where we have two baseball teams, the green team and the red team, playing 5 games. The diagram below is my preferred way to make what's called a tree diagram. The dots, or vertices, represent games to be played, and the segments, or edges, they're sometimes called, coming out of the dots, represent the winner of the game. So each sequence of 5 games could be represented by a string of 5 letters. So, for instance, that sequence of games would be represented by this. Green won the first game, red won the second game, green won the third game, red won the fourth and fifth games. Now notice, again, in this diagram, the dots represent games to be played. In general, it could be an experiment to be run or a choice to be made. So again, in my preferred way of making these tree diagrams, the dots represent choices to be made or experiments to be run, and then the segments or the edges emanating from those dots indicate the winner. Now notice that each string like this corresponds to a possible sequence of games, and so we have a choice of G or R to go there, another choice of G or R to go there. We have 5 times that we get to choose either G or R. So 2 times 2 times 2 times 2 times 2, that's 2 to the 5th, is 32 possible 5-game sequences. So each of these final segments represents the final segment of a 5-game sequence. So there are 32 segments down here at the very bottom. The diagram below is the way the author of our book makes a tree diagram. The vertices represent the outcome of the experiments. In this diagram, a dot represents the winner of a game. The edges don't really play a role. So, for instance, this dot represents the winner of game 1. So in this diagram, the edges don't really play a role. All the information is in the dots. And notice the first dot doesn't really do anything. It just indicates that you started something. So I don't really like this way of making trees, but it's what the author does, so we'll make trees this way. Notice that the very bottom of the diagram is terminated with dots. Those dots are in the last row for the winner of Game 5. So let's do a more sophisticated example. Let's consider a series where the winner is the first team to win 3 games. So once one of the teams wins 3 games, then the series is over. Notice that this sequence is a sequence that the green team wins, whereas this sequence is a sequence that the red team wins. So some of the sequences just have 3 games, like that one. Some of the sequences can have 5 games. This sequence went on for 5 games before the red team finally won. Notice that there are not as many possible sequences. If you count the number of dots that represent the end of a sequence where one team or the other has won, there are only 16 possible sequences. The author of the book would say that there are 16 ways for the series to be played. Now consider a different format for the series, one in which the first team to get either 2 games in a row or to win 3 games total wins the series. So this sequence is one in which the green team wins after only 2 games. That red circled sequence is one in which the red team finally wins after playing 5 games. Notice that if you count the total number of possible sequences, there are only 8 of them. Let's do another example. In the Major League Baseball World Series, the first team to win 4 games wins the series. So question A, suppose the green team wins the first 3 games. How many ways can the series be completed? Make a possibility tree to illustrate. Now, so far, my possibility trees have been oriented vertically, simply because of the landscape orientation of my paper and the fact that my trees were going to be quite wide. I decided to orient them that way. The book tends to orient trees horizontally, so I'll do that for this one. So I'm going to show the starting situation where the green team has won 3 games. So there's the situation where the green team has won the first 3 games. Notice that the first dot doesn't really do anything but just simply indicate that the series has started. From here on, the tree has to have branches indicating who wins the subsequent games. So there's the possibility tree. Notice that after this 3rd game, if green wins another game, then the tournament is over. So there are all these sequences that end with green finally winning a 4th game. There's one sequence that ends with red winning 4 games in a row to end the series as the winner. So the question, how many ways can this series be completed, is answered by looking at the tree diagram and seeing how many terminal dots there are. There are 5 terminal dots. 4 of them are green, indicating that green wins the series, and 1 of them is red, indicating that red wins the series. Question B. If all outcomes are equally likely and the green team has won the first 3 games, what's the probability that the red team will win the series? We answer this using the equally likely probability rule. So the probability that red wins is 0.2, 1/5. Let's go on. Next, I want to talk about the multiplication rule. It's stated in Theorem 9.1. If an operation consists of k steps, and the first step can be performed in n subscript 1 ways, and the second step can be performed in n subscript 2 ways, regardless of how the first step was performed, and so on, all the way down to the kth step can be performed in n subscript k ways, regardless of how the preceding steps were performed. Then the entire operation can be performed in this many ways. It's simply the product of all those n subscript i's, for I goes from 1 to k. So that's where we get the title, the multiplication rule. You count the number of ways for each of the steps, and then you multiply those numbers together to get the number of ways to perform the entire operation. So, for example, example 3, let's consider the situation with Ohio license plates. They have the form letter, letter, number, number, letter, letter. So the question is, how many possible license plates are possible? Well, let's go back up and look at the multiplication rule again. The multiplication rule refers to steps and how many ways that step can be performed. I prefer to think of tasks, so I'll present my solution in terms of tasks. Now, it will help to visualize our tasks. We could think about having to populate 6 blanks. So we have to fill those 6 blanks with characters. The first 2 have to be letters, which I'll denote A1 and A2. The third and fourth blanks have to be filled with numbers, which I'll denote with number sign 1, number sign 2, and so forth. So our tasks there's a table that shows all the tasks that we have to do to fill those blanks with characters. And you see that there are those n subscript I symbols that denote the number of ways of completing those tasks. So the total number of ways is simply the product of those numbers. Total number of ways is 45,697,600. Let's go on. Question B, how many possible plates if no character can be used more than once? Well, it will be simple to just simply go up and grab the work that we just did and modify it slightly. So I'm going to copy all this stuff and drag it down to the next page, and we'll find it there when we scroll back down. So there's the work we did on the previous page, copied and brought back down here. Now, the fact that no character can be used more than once means that when we choose character A2, the second letter in the sequence, we don't actually have 26 letters to choose from. We only have 25, because we can't choose the same letter that was used for character A1. Similarly, when we get around to choosing the second number, we don't really have 10 numbers to choose from. We don't have 10 digits. We only have 9. And when we get around to choosing the fifth and sixth characters in the sequence, letters A3 and A4, we don't have 26 letters to choose from. We have 24 and then 23. So the total number of ways gets modified. So the total number of ways goes down to only 32,292,000. Let's go on. How many possible plates could begin with OU? Well, again, let's start by copying the work that we just did. So I'll copy this and I'll drag it down, and when we scroll back down, we'll find it. Okay, there's the work that we did in question B, dragged down to here. Now we have to have a plate that begins with OU. So that means that we only have one possibility when choosing the first letter. It's got to be an O. And the second letter also has to be a U. So N1 and N2 just become the number 1. Now what about the number? Well, we have 10 ways of choosing the first digit. Now this problem statement does not say that repetition is not allowed, so we should assume that repetition is allowed. So when we get around to choosing the letters for A3 and A4, we have 26 letters to choose from for each of those. So the result is that there are 67,600 license plates available that begin with OU. Let's go on. Example 4, the number of ways to seat a group. 7 people are sitting together in a row at a soccer game. How many ways can they be seated together in the row? Well, we can again think of blanks to be filled. And tasks that are filling those seats. So our tasks are to fill those seats. We have to choose a person for each of those 7 seats. So that's 7 tasks. Now the number of ways of doing that, well, choosing the first person for seat 1, there are 7 ways because there are 7 people to choose from. But once we've chosen that person for seat 1, that person can't be the person in seat 2, so there are only 6 people left to go in seat 2. And then there are going to be only 5 people left to choose from to go in seat 3. So we see that the number of ways is this sequence of numbers. So the total number of ways is the following. The total number of ways is 5040. And notice that that's 7 factorial. Let's go on. Question B. Suppose it's a family that's being seated, and they want to sit with the parents on the end, with the mom on the left, and the 5 kids in the middle. How many ways can the family be seated? Well, let's go back up and copy the work that we just did, and I'll copy it down below, and when we scroll back down, we'll find it. All right, there's the work that we did in the previous question A. Now let's modify this. We want to have the mom on the left, and then the dad will be on the far right, or the other parent of whatever gender. So the number of ways we can choose the person for seat 1 is just 1. And the number of ways we can choose the person for seat 7 is just 1. But the seats in between, the number of choices for seat 2 is, well, we have 5 kids we can choose from for seat 2. For seat 3, we're only going to have 4 kids left to choose from. So the total number of ways is 120. Let's go on. Question C. Suppose that it's a family that wants to sit with the parents on the end, but with no preference for who sits on the left, and then the 5 kids in the middle. So in this case, how many ways can the family be seated? Well, we get to choose a parent for seat 1 and a parent for seat 7. But we get to decide which parent sits in seat 1. So there are 2 choices for who goes in seat 1. Once you make that choice of which parent goes in seat 1, then you don't. There's only one way to choose who goes in seat 7. So N1 is the number 2, N7 is the number 1. The kids, we have 5 kids to choose from for seat 2, 4 kids to choose from for seat 3, and so on. So the total number of ways in this case is 540. Question D. Suppose that it's a family and the parents want to be seated together with no preference for who sits on the left. In this case, how many ways can the family be seated? Well, this gets kind of tricky. We have to choose where the parents are going to go, either there or there or there, for instance, and which parent is going to be seated on the left. So our first choice should be choose which seat the leftmost parent will be in. So we have to choose which of these seats the leftmost parent is going to go in. Well, we can't actually choose seat 7 for the leftmost parent because there's got to be somebody sitting to that parent's right. So the leftmost parent needs to go in one of those 6 seats. So there are 6 ways to complete this task. Then the next thing we need to do is choose which parent is going to be the leftmost parent. Well, there are 2 parents, so we have 2 choices for who's going to be the parent sitting on the left. Now, we don't know where the parents got seated. They could have gotten seated here, they could have gotten seated here, whatever. All we know is that there are 5 remaining seats to be filled. So those seats are going to have to be filled with kids. And furthermore, we can't describe them by seat number. We can just say the kid on the far left and so forth. So all we know is that whatever seats are available, we'll put a kid in the leftmost seat that's available. And then we'll choose the next kid to go in the next seat, and so on. And in the end, the last kid we choose will be the kid that's on the most right seat of all the kids. Well, we have 5 kids to choose from for the leftmost kid, and then 4 for the next kid, and so on. So the total number of ways is 1,440 ways. Let's go on. Example 5. This is similar to 9.2, number 17. How many integers are there from 100 through 999? Well, this is a blast from the past. In the previous video, we talked about the idea of counting items in a list. My solution was the following approach. There's a list of all the integers starting with 1 and going through 999. Now the integers that we want are the ones that start with 100. So we're interested in that green batch of numbers. The simplest way for me to think about counting them is this. Count the number of numbers in the whole list and subtract the numbers that we don't want. We get a total of 900 integers. Now we can put this in agreement with the theorem that we discussed in the previous video. Let's call this first integer that we want to keep the letter m, and the last integer that we want to keep the letter n. And what we have here is n minus the quantity m minus 1. Let's go on. Question B. How many integers from 100 through 999 are even? Well, we can think of this as a choice problem. Now, we could have also done this with the previous problem. We could think of this in terms of choosing digits. So I'm going to imagine filling these blanks with digits. Now I'm starting with the rightmost digit because we have to have an even number. So that digit that goes in that rightmost spot has to be 0, 2, 4, 6, or 8. So that's 5 ways of filling that rightmost spot. I'm calling that digit D subscript 0 because that's the ones position. 1 is 10 to the 0. Now we have to imagine filling the next blank, the tens digit. 10 is 10 to the 1, so that's why I've called that digit D1. Well, the number of ways that we can fill that spot is 10 because we can choose 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Any of the 10 digits can go there. Now let's imagine filling this spot. That can't be any of the 10 digits because we can't have a 0 as the first digit. The digit can be 1, 2, 3, 4, 5, 6, 7, 8, 9, so there are 9 ways of filling that spot. So the total number of ways is 450. Hey, let's imagine doing this in the previous problem. The previous problem, we found that there were 900 integers from 100 through 999. So I'm going to copy this solution that we just did and put it on the previous page. When we scroll up, we'll find it there. So there we are back in question A. So I'm going to add this second solution. So task number 0, choosing digit D0, we have 10 ways of doing that task. 10 ways of choosing that that D0 on the far right. 10 ways of choosing that digit, only 9 ways of choosing that digit, for a total of 900 possible ways. Question C. How many integers from 100 through 999 have distinct digits? Well, let's go back up and copy the solution from question B and bring it back down. I'll do that, and when we scroll down, we'll find it. So there's a copy of the work that we did in B. Now, we have to approach this in a different order from what we did before. We should start by choosing the leftmost digit because that digit cannot be a 0. So we have to make sure that we get that digit chosen correctly. So when choosing the digit D2, that's our first task, there are only 9 digits available to choose from because that digit D2 cannot be a 0. Now, what about when choosing digit D1? Well, we can't choose the same digit that we chose for digit D2, but we do have the option of choosing the number 0 for the digit. We didn't have that option before. So actually, the number of ways of choosing the middle digit is also 9. Now, finally, when we get around to choosing, this should be digit D0, when we get around to choosing the rightmost digit, well, we have 8 numbers left to choose from. So the number of ways is 648 ways. Let's go on. Question D. How many integers from 100 through 999 are even and have distinct digits? Well, this is actually a very tricky problem. Let's think about this in terms of tasks. We have to choose digits D0, D1, D2. Now think about the possibilities for D2. D2 can be any of the numbers from 1 to 9. Now think about the possibilities for D0. D0 can be 0, 2, 4, 6, 8. So there are only 5 possibilities for D0. Now the trick is that the choice for D0 depends on the choice for D2. If I happen to choose an odd number for D2, then I will still have 5 choices of even digits that it can go for D0. But if I happen to choose an even number for D2, then when I get around to choosing D0, I'm not going to have 5 digits to choose from. I'm going to have only 4 digits to choose from. So I really have to count 2 different groups of numbers. In the first case, we choose an odd number for D2. Well, that means D2 could be 1, 3, 5, 7, 9. So 5 choices for N1. And then the second thing we do is we choose D0. Now, since an odd number was chosen for D2, that doesn't affect our choice of D0. D0 has to be even, so it's got to be 0, 2, 4, 6, or 8. So there are 5 choices for D0 as well. And then when we choose the middle digit, there are 8 digits left. So our total number of ways is 200. 200 numbers from 100 through 199 that are even and have distinct digits and have an odd digit D2. Now what about the case where D2 is even? Well, then when we choose D2, that's our first task, we have, well, let's see, D2 would have to be 2, 4, 6, or 8. D2 could not be the number 0. So there are only 4 ways of doing that. Now, the second thing we would do would be to choose digit D0. Now, it could be 0, 2, 4, 6, or 8. That's 5 even numbers. But one of those has been chosen as the digit for D2. So there are actually 4 ways of choosing digit D0, because we have one digit that's unavailable because it's already been chosen to be the digit that goes in D2. And then when we get around to choosing the middle digit, there are 8 numbers left. So the total number of ways is 128. So the total number of integers overall is this batch and this batch. So the total number is 328. Let's go on. Question E. What's the probability that a randomly chosen 4-digit integer has distinct digits? Well, that's going to be the number of those 4-digit integers of that type divided by the total number of 4-digit integers. So we should introduce an event. So then the probability of E will be the number of elements in E divided by the number of elements in the sample space. Well, let's see. This event was counted. Now I see I've got a typo here. This should be 3-digit integer. So that was counted in question C. We found there's 648 ways for an integer from 100 through 999 to have distinct digits. And the number of items in the sample space, that's the total number of 3-digit integers, that was 900. So the probability is 0.72. Question F. What's the probability that a randomly chosen this should say 3-digit integer, is even and has distinct digits? Well, let's define that to be event F. So the probability of F will be the number of elements in the event F divided by the number of elements in the sample space. Well, we counted the number of elements in event F in question D. We got 328. So the probability is roughly 0.364. Well, that's the end of that very long example. Let's go on. Question 6, counting the iterations of a loop. So in this problem, we're going to consider this algorithm segment for I going from 5 to 50, and then for j going from 10 to 20, we're going to perform some statements in the body of the inner loop. So in other words, there's I has some value and j has some value, and the statements in the green inner loop get performed, and then j gets incremented, the statements in the inner loop get performed again, j gets incremented, and so on, all the way up until j gets to 20. And then I gets incremented, and we do the whole thing again. So the question is, how many times will the innermost loop be iterated when the algorithm segment is run? Well, think about this problem in the following way. For every pair of numbers, I and j, that fit these requirements, that innermost loop is going to be run. So what we need to do is we need to count the number of pairs of numbers, I and j, such that I is in this set and j is in this set. So we need to count those pairs. Well, the number of pairs will be the number of choices for I times the number of choices for j. Now here we can use that theorem. The number of choices for I is going to be 50 minus 5 minus 1. And the number of choices for j will be 20 minus 10 minus 1. So here we're counting the number of integers from 5 to 50 inclusive. And here we're counting the number of integers from 10 to 20 inclusive. So the result is that the innermost loop will be executed 506 times. Let's go on. Question 7. In this question, we're going to be counting relations and functions. Suppose A is a set with m elements and B is a set with n elements. How many elements are in the Cartesian product A cross B? Well, the solution is to remember that the Cartesian product is the set of ordered pairs. So we want to count the elements in the Cartesian product. We just have to count the number of such ordered pairs. So let's think of a task of building an ordered pair. So my total number of ways is m times n. Notice that I could not call this total number of ways n. I had to call it k. It's because n was already taken. So I had to use the letter k for my number of ways. Go on. How many relations are there from A to B? Now remember what a relation is. A relation is a subset of the Cartesian product. So every subset of the Cartesian product could be thought of as a relation. So if I want to count the number of relations from A to B, I have to count the number of subsets of A cross B. Well, how do I count the number of subsets? That seems really hard. So let's think of it this way. Let's think of the task of building a subset of A cross B. So we're going to consider the task of building a subset of A cross B, and that subset is going to be called R because we're going to be thinking of that subset as a relation. Now, we have a bunch of choices. What are our choices? Well, let's go back up and recall what we did in question A. In question A, we found that the total number of elements in the Cartesian product is this number, m times n. So that means that there are m times n ordered pairs. So there are m times n ordered pairs of the form A, comma B in the Cartesian product A cross B. Well, for each of those elements, each of those ordered pairs, we get to decide, is that ordered pair going to make it into our subset R or not? Is it going to be included or not? So our task is to decide whether or not that ordered pair A, comma B subscript 1 is in the relation. There are two ways of doing that task. Either that ordered pair could be included or it could not be. The second task will be to go to the next ordered pair. That ordered pair could be included or it could be excluded. So there are two ways of making that decision. And we keep going until we go through all the ordered pairs. We get to the very last ordered pair, it's going to have a subscript m times n. We get to decide whether that's going to be included in our subset. That's our relation. Now I should label each of these. So the total number of ways will be will be 2 raised to the m times n power. Because again, for each element of the Cartesian product, A cross B, we get to decide whether or not that ordered pair is going to be in our subset. That's our relation. So the total number of relations from a set A to set B is 2 to the m times n, where m is the number of elements in set A and n is the number of elements in set B. Question B, how many functions are there from A to B? Well, remember, a function from A to B is a relation, but it's one that for each element of A, there's exactly one element of B that's the output. So a function takes as input an element of A and produces as output an element of B. So how do we describe a function? If we want to build a function, we get to choose a bunch of things. We get to choose an output for each of the inputs. For each of the elements of A, we get to choose an output that's an element of B. So we have a bunch of tasks. So, for instance, for the input A subscript 1, we get to choose an output. It can be anything in set B. So the number of ways of doing this first task is n ways, because there are n elements in set B that we can choose from. Now we get to choose the output for the input A subscript 2. Well, the number of ways will again be n. And so forth. Every time we choose an output, we have n choices. So the total number of ways will be n raised to the m power. N is the number of elements in set B, and m is the number of elements in set A. Question C, how many one-to-one functions are there from A to B? Well, that's going to be the same approach. In fact, we can copy down our approach from question C and bring it up here, or bring it down here. So let's copy all this stuff and bring it down. I'll do that, and when we scroll back down, we'll find it there. So there's our work from question C, copied and brought down here. Now, for a one-to-one function, no output can get used more than once. So that'll affect the number of ways that we can do these tasks. When you choose the output for input A subscript 1, there are n ways of doing it. N elements of set B. We can choose any of them as the output. But when we choose the output for input A subscript 2, we don't get to choose any of those elements of B. We can only choose n minus 1 of them. And so forth, all the way down to the last one. We'll be able to choose the last output this many ways, n minus the quantity m minus 1. So the total number of ways will be that. Now, there's another way of writing this. This can be written as n factorial divided by n minus m factorial. You can check this, that this expression really does give you this. Let's go on. How many functions are there from a set with 7 elements to a set with 3 elements? Well, that's just a special case of what we did in question C. The number of functions from a set with from a set A to B is n to the m, where n is the number of elements in set B and m is the number of elements in set A. So there are 2187 functions. Let's go on. Now I want to talk about permutations. A permutation of a set is a choice of an ordering of the elements of the set. And what's called an R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. So if your set has n elements, then what we were calling just a permutation of a set is the same as saying an n permutation of the set. That is, you'd make an ordered selection of all of the elements of the set. And we introduce a symbol. The number of R permutations of a set of n elements is denoted by this symbol, capital P parentheses n comma R. Now this notation is new, so let's play with it a little bit. Question A is to give examples of 3 permutations of the set A, B, C, D, E, F, G. Well, a permutation of that set is a choice of an ordering of the elements of the set. So here we go. One permutation of that set is just that choice of ordering. Another one could be, let's see, it could reverse them. That's another ordering. Another ordering could be just change the first 2. So those are 3 permutations of that set. Question B, give examples of 3 hyphen permutations of this set. Well, a 3 hyphen permutation, or just spoken, a 3 permutation, is an ordered selection of 3 elements. So I need to choose 3 elements of that set along with an ordering for those 3 elements. So those are some examples of 3 permutations. I've given 2 of them. Each of those is an ordered selection of 3 elements of that set A, B, C, D, E, F, G. Let's go on. For the set A, B, C, D, E, F, G, how many permutations are there? Well, let's think of this as a task. To build a permutation, we have to choose a letter to go in each of those 7 blanks. So we have these 7 tasks, that is, to choose each of those letters for those blanks. The first letter, we get to choose any of the 7 letters. But when we get around to choosing the second letter, we can't repeat a letter, so there are only 6 ways. So there are 7 factorial, or 50-40 permutations of that set of 7 elements. Question D, for that same set, how many 3 permutations are there? Well, here we can actually copy down some of our tasks. So to build a 3 permutation, we need to choose 3 letters in an order. So there are our tasks, the descriptions of those tasks, and the number of ways. So the total number of ways is 7 times 6 times 5, which is 210. But it's interesting to think about this expression. 7 times 6 times 5 could be thought of as 7 factorial over 4 factorial. These two examples, C and D, set us up to understand the following theorems. The counting the number of permutations. For any integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. So we saw that at work in question C. Theorem 9.2.3 says if n and r are integers and 1 is less than or equal to r, which is less than or equal to n, then the number of r permutations of a set of n elements is given by this expression, which can be achieved by doing this: n factorial over n minus r factorial. We did that in in question D of the previous example. Let's do some examples of computing a number of permutations. So the formula we're going to use is that. So p parentheses 5 comma 3 the number of those permutations is 60. For the next one, p parentheses 5 comma 1 we just get the answer of 5. P parentheses 5 comma 5 we get an answer of 120. Remember that 0 factorial is not 0. 0 factorial is the number 1. And finally, p parentheses 5 comma 0. Let's go on. Our final example is this abstract example. Prove that for all integers n greater than or equal to 3, this equation is true. Well, let's work on the left side. So there are our factorial expressions, and notice the obvious cancellations. This cancels that. This cancels that. So we end up with these truncated factorials. Now, how can we simplify this? Well, notice that there's a common factor in these two expressions. There's an n and there's an n minus 1. So let's factor that out. So we pull that out front, and then we put in parentheses what it leaves behind. What it leaves behind is this expression n times n minus 1 times 3. Now let's look at the right side of the predicate. So we see that the right side of the predicate equals the left side, so the statement is true. So since the left side equals the right side, the predicate is true, and so we've proven our statement. Now, think about something though. Where did we use the fact that n is greater than or equal to 3? Think about what goes on in the denominators. In that expression, there's an n minus 2 factorial, and there's an n minus 3 factorial. Down here, there's an n minus 2 factorial. We're allowed to have 0 factorial, so we could have n be the number 3, and we would have 3 minus 3 would be 0, so we'd have 0 factorial. But you cannot have a factorial of a negative integer. So that's why n has to be greater than or equal to 3. So all of this stuff that we wrote, we're only assured that it's defined when n is greater than or equal to 3. So this predicate is true only when n is greater than or equal to 3. When n is not greater than or equal to 3, this predicate is not even a defined expression. Well, that's the end of this example, and that's the end of the video. Thank you.